Okay, today I want to continue our discussion of dienes, by now transitioning to those that are conjugated with pi systems, like we said last time, which are delocalized or in resonance with one another. And we'll first, before we talk about reactions, do a brief molecular orbital MO analysis. So if you consider butadiene, you could call it buta-1,3-diene. But if it's conjugated, then they must be at positions 1 and 3. This alkene, like we said last time, has 4 parallel p orbitals, or they are at least parallel in its ground state. And so the molecular orbital analysis is going to take into account the fact that it's not just these two, C1 and C2 p orbitals that interact. It's not just 3 and 4. It's really all 4 p orbitals that are sharing pi electron density. And they do so by overlapping or mixing to become pi molecular orbitals. So here we see that there are 4 p orbitals. There are 4 pi electrons, 2 in each pi bond. And the number of p orbitals that mix will be the number of molecular orbitals that we make, or 4 molecular orbitals. So you can simply go about drawing a molecular orbital energy diagram by considering all of the possible ways that these could overlap in a pi-like or parallel manner. So one possible combination is to have all of them in phase, so the wave functions are constructive. And this is the lowest energy molecular orbital, what we call psi1, or pi1. Alternatively, you could have carbons 1 and 2 interacting in a constructive manner, while 3 and 4 are out of phase with 1 and 2. So that's pi2. There will be an associated orbital with which we fill pi electron density as we go up in energy. I'll draw 2 more. So pi3 would be if the C2, C3 p orbitals are in phase and the others are not. And finally, pi4, the highest energy molecular orbital, is going to be when we have all consecutive p orbitals out of phase, or the phasing consistently alternates. So because there are 4 pi electrons here, we put 2 in the lowest energy molecular orbital and 2 in the next lowest. And you can divide these in half to think about those that are bonding. Those are below this dotted line, where they lead to stabilizing interactions between the nuclei. And those that are anti-bonding are psi3 and 4. Excuse me, pi3 and 4. And these are unoccupied in the ground state, or the lowest energy electronic configuration. So another way to analyze this is to think about the highest occupied or the lowest unoccupied molecular orbitals. And I'll use colors here to indicate the most energetic orbital that is filled with electrons, or the highest occupied molecular orbital, is pi2, where you have a single node where the phasing is mismatched. So to think about the number of nodes in each of these, you just draw a dotted line for every time the phasing doesn't agree. The lowest energy orbital has 0 nodes, while pi2, we said, has a single one in the center between C2 and C3. There are 2 nodes in pi3, and there is a node between every consecutive p orbital in pi4. So if there are 4 p orbitals, or 4 molecular orbitals, you'll find that the highest energy one always has one less node compared to the total number of molecular orbitals, or n minus 1. So the HOMO, or the highest energy molecular orbital, is going to be that which can donate electrons, or this is what we think of as the nucleophilic orbital associated with the diene. However, if the diene were to behave as an electrophile, which it generally does not, but if it did, then we would consider the lowest unoccupied molecular orbital, or the LUMO. And that one can accept electrons. That's the electrophile. So we're going to do a series of reactions where the diene is reacting with a variety of electrophiles. And what we'll find is that during step 1, it is always this highest energy molecular orbital, or pi 2, that reacts fastest. So let's do some examples related to those mechanisms with electrophiles. So I want to start with a generic example where you have a reagent that has an electrophilic atom bound to a nucleophilic one. And we know that our alkene, right, is a nucleophile. And therefore, the electrophilic end of this reagent will react first with said nucleophile. So what you do is you start by numbering the conjugated carbons of the alkene system. So in this example, every single carbon is part of the diene, but later examples will have other sp3 centers that are not participating in resonance. And you can number it 1 through 4 from left to right or right to left. If it's symmetrical, it does not matter. What you want to do is always first add the electrophile to one of the two ends, one of the termini, either C1 or C4, and you don't have to try both unless it's not symmetrical. So adding the electrophile to C1 gives an intermediate that's a carbocation. So the nucleophile, or the eventual nucleophile, is now in solution. That serves as a leaving group. And this carbon 2, the internal carbon, had a single hydrogen, and it still just has one hydrogen. And therefore, that is a carbocation. So you always will generate an allylic. Allylic means one away from a pi system, generally a CC pi bond, carbocation. So that carbocation must be on one of the internal carbons, that which is closer to the other pi bond, C2 or C3. So in this case, we have added our electrophile to C1, and we have a carbocation on C2. The reason that must be allylic is that allylic cations are stabilized by resonance. So I'll draw that resonance form below. If you simply push the nucleophilic neighboring pi bond, it'll develop between carbons 2 and 3, rendering a positive charge on what we called carbon 4. Right? Carbon 4 has a CC double bond, and therefore 2 hydrogens. It still just has 2 hydrogens. So when it has a CC single bond, it has an empty p orbital. And of course, these are 2 simple elementary ways to explain a molecule that's more complex, right? Or what we know as the hybrid molecule. So the hybrid structure is a weighted average of these 2, where there's pi character not just between carbons 3 and 4, not just between 2 and 3, but there's always pi electron density between those 3 carbons. And the positive charge, therefore, is delocalized, with a greater amount of positive charge on the carbon that is more substituted, or carbon 2, which better stabilizes positive charge. What this means is the nucleophile could attack either position. If the nucleophile attacks the terminal carbon, we call that 1,4 addition. The pi bond remains between carbons 2 and 3. If it were to attack carbon 2, the cation we had before we drew the resonance structure, then you would have a simple 1,2 addition. Forgive me, I've simply flipped the structure over here, but this is carbon 1 and 2. They are adjacent nucleophile and electrophile, like any typical electrophilic addition to an alkene. So you can get two different isomers. And we'll talk extensively next about how we select between these in terms of which one is the predominant product. But the relationship between them is they are structural isomers. In reaction chemistry, we call these regioisomers. And which one is favored is going to depend on the conditions of the reaction. It will depend upon whether the reaction is under kinetic, which means the faster product wins, or thermodynamic, which means the more stable product wins. Which one of those conditions is controlling the reaction will tell you if it's 1,4 or 1,2 that is major. So that will dictate regioselectivity. So next, let me do a brief introduction to this concept of kinetic versus thermodynamic control, which we will see as a theme throughout the course, and that it dictates regioselectivity and stereoselectivity for multiple reactions. But first, we'll do it with 1,2 and 1,4 additions. So a very, very common misconception in sophomore organic chemistry is that the more stable product always forms faster. Those are two different statements. It's true that about half the time, actually, the more stable product forms slower. And it depends upon the reaction conditions as to whether the fast product, the kinetic one, or the stable product, the thermodynamic one, is favored. So kinetic is all about speed. It doesn't care about where the final product is in terms of energy. It's all about what's the most stable transition state. Transition state is indicated by double dagger. Thermo is all about stability, not of the transition state, but stability of the final product. So kinetic control is generally indicated by one or two reaction conditions. Low temperature and or short reaction times. And there's no general rule for what's a low temperature for all reactions. It's reaction specific, but we'll make that very clear in the examples. So low temperature and short reaction times indicate that we are under irreversible conditions, or the reactant reacts to form product, and whatever happens first is the reaction that happened fastest, and you're stuck with the product. It doesn't matter if the product's stable or not. It's all about the fastest route to get to product, and it happens once. Thermodynamic control is indicated by conditions that are the opposite. Those that are high temperature and or long reaction times. When you have a higher temperature, you raise the kinetic energy of the molecules in solution, and they can collide more frequently and with higher energy. What that means is the reaction becomes more reversible, or the molecules can equilibrate back and forth. It can overcome the transition state from left to right and right to left, or you are under reversible equilibrium type conditions. In this case, at high temperatures, the faster product, the kinetic product, still forms first, or early in the reaction, you'll observe the kinetic product. But if you let it sit and go back and forth, it's always going to give you the product that is most stable in the end. So, one rule you can rely on is always being true in this course is that for 1,2 and 1,4 additions, the 1,2 product is always the faster or the kinetic product. And this has to do with the proximity effect. So if you think about the transition state where the pi system is breaking, forming a bond to the electrophile at C1, C2 is right next door. The electrophile is breaking away from eventual nucleophile. That nucleophile will more rapidly attack C2 simply because it's closer in space. So that's known as the proximity effect. So you get the 1,2 product early in the reaction, or if you have low temperature, that's your major product. However, if the reaction can go forwards and backwards in reverse, meaning the nucleophile can fall back off, then you may get 1,2 or 1,4. So thermodynamic could be 1,2 or 1,4. It depends on the specific diene that you're using. But what I can tell you is always true is that the thermodynamic product is always the most stable final alkene. So let me make sense of this via reaction coordinate. And I'll just consider that reaction that we did in the previous example. Free energy is a function of reaction progress or coordinate. And so we had butadiene with some hypothetical electrophilic reagent. And addition of the electrophile to C1 gave this single intermediate, the hybrid resonance form, where the nucleophile is next door and ready to trap. And that's the slow step. However, there are two alternate paths you could take. The kinetic path goes over a low transition state and leads to a final product. We said that was 1,2. So we would call this the kinetic transition state and the kinetic product. However, in this example, the 1,4 product is the thermodynamic one, but not always. It goes over a higher transition state, meaning it is slower to form. The nucleophile must detach and then attack carbon 4 more slowly to yield the final alkene. That's your thermodynamic product and your thermodynamic transition state. Now, both of these transition states here are generally lower in energy than initial carbocation formation, which is very endothermic and rate limiting. The reason that this is the thermodynamic alkene is because you have two secondary carbons, or it's the more substituted alkene. In other words, both carbons here, both sp2 centers, are secondary, whereas here in the kinetic product, one of them is primary, or that's mono-substituted. And so we would say for this example that the 1,4 product is the one that is going to predominate under reversible conditions. If you have a high temperature, it can go back over this red hill here and overcome the thermodynamic barrier with enough time. If you run the reaction quickly and you stop it after 20 minutes, or you do it at a very low temperature, or both, it's just going to go over the red hump more quickly, and you'll be stuck at the kinetic product. So thermodynamic is all about where you end. Kinetic is all about the path you take to get there. So let me do one or two more examples just to indicate some of these themes. So let's try one where we have a diene system that is conjugated, but it's not symmetrical this time. Which means you need to make a conscious decision about which carbon is going to attack the electrophile faster, or which double bond is more nucleophilic, essentially. So I'll just treat this with HCl, but the same argument would be true with HBr, Br2, Cl2, any eventual electrophile. So what I notice here is, first of all, when we add that electrophile, or we add the H plus to this diene, it's going to have to go on C1 or C4, because we want the carbocation to be on 2 or 3. Once again, so the carbocation can be allylic and thus resonance stabilized. So what I see is that the secondary carbon, carbon 2 is a tertiary center. It has 3 bonds to carbon. 3 sigma bonds, that is. Whereas carbon 3 is a secondary center. So what that means is that the pi bond bearing a tertiary center will react faster to form a tertiary carbocation. So the C1, C2 pi bond is broken, and it generates a carbocation at position 2. The next step is to draw your resonance structure. And resonance does not take time, of course. It's just a phenomenon we use to explain a more complex molecule. But here, we simply push the adjacent pi bond and show this allylic resonance form where the positive charge has skipped from carbon 2 now to carbon 4. Okay. If you can't draw a resonance structure, that means you added the electrophile to the wrong position. So eventual trapping with bromide or chloride generates 2 products. The 1,2 product, where we have left the disubstituted double bond intact, or the 1,4 product. And we know 1,2 is always faster. That would predominate at low temperature, like -80. And the 1,4 product, in this case, is thermodynamic as well. Because here you have a tertiary center and a secondary center, or that is a more substituted double bond. Whereas the olefin that's retained in the 1,2 product has 2 secondary centers, and therefore it's less stable. So this is another typical example of where one of them is kinetic and one is thermodynamic. However, I want to finish this section with one example where that's not true. So this diene is also not symmetrical, which means you can number it 1 through 4 from left to right or right to left, and you need to decide which carbon, is it 1 or is it 4, that is more nucleophilic. So let's try both, because it's not so clear in this example. If you were to protonate C1, that would leave a carbocation on C2. Alternatively, if you were to protonate not C3, I know you want to make a tertiary carbocation on C4, but you protonate C4 regardless. The hydrogen or the electrophile must go on the end. The 1,2 pi bond stays intact. You would get a secondary but allylic resonance form. So now you should draw the resonance structure for each. Where this pi bond is simply moved between what was 2 and 3. And now we'll push the 1,2 pi bond So to decide which one of these intermediates forms faster, we need to consider which one is more stable according to Hammond's postulate. This uphill step will proceed more quickly if it's less uphill or if it makes a more stable carbocation. And this one is secondary allylic in resonance with tertiary allylic. However, below we have secondary and primary, which means that the more substituted pair of resonance structures is more stable, and that will lead to the product. So let me erase the other theoretical protonation so we can have room for the final products. So trapping with bromide gives this 1,2 product where the hydrogen has added to carbon 1 and bromide trapped carbon 2, whereas after you draw the resonance structure, the bromide and new hydrogen are at positions 1 and 4. And we know that this is kinetic because 1,2 is always faster from the proximity effect. However, also in this case, the alkene, which is a secondary and tertiary, or a tri-substituted alkene, that is more stable than this secondary, or di-substituted alkene. Which means that this 1,2 product is both kinetic and thermodynamic. And you don't get this one at any temperature or for any reaction time. You don't have to be told the temperature because you always get the 1,2 product. It is possible that 1,2 is both kinetic and thermodynamic in some cases. And it's generally this case here where carbon 4 is tri-substituted. It's actually the 1,2 pi bond that reacts faster